Okay. And it's gonna work and focus right. There we go. All right, let's talk about gravitation, specifically universal gravitation. So the equation for the force due to gravity anywhere in the universe is big G m1 m2 over r squared, where these are the masses of both objects. Mass of object 1 and mass of object 2. Both play a part when it comes to force of gravity anywhere in the universe. This is the distance between the center of the two objects. Not always the radius. Rarely the radius. Sometimes the radius, but not always the radius, even though it's got that silly little r in there. All right. And then G, this is something you definitely don't need to memorize, but this big G is 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Note, this times 10 to the negative 11 means that gravity is weak unless the objects are very large. That's why we feel gravity from Earth, because Earth is really, really big. Very, very, very massive. Now, we've used another force due to gravity equals mg, and this works only on one specific planet. Like for instance, on our planet, this is 9.81 meters per second squared. But you can't take this and go to the moon and use the same equation, where you say, okay, I want to know the force of gravity of myself on the moon. I need to know, I know my mass. I know 9.81 meters per second squared. Therefore, I know my weight on the moon. That's not how it works. Weight and force of gravity are used interchangeably. What you need to know is that little g for anywhere. And you could figure that out as well. In fact, because both of these are equal to each other, we can set them equal to each other. We can call this mg equals big G m1 m2 over r squared. In fact, this m1 is the mass of the object, right? If we want to define the mass of me, my weight on Earth, it would be the mass of the object. And then this would be the mass of, I'm going to call it like the planet, MP. So MO equals mass of object. And MP equals mass of planet. Or, more broadly, object causing acceleration. In our case, it's the planet. But because we have mass on both sides, they're both gonna, the mass of the object on both sides, they're both gonna cancel. And as such, little g is just equal to big G times the mass of the planet divided by the distance between the two centers squared. And remember, if you knew this around a planet, say you were, you know, you were out here, or a satellite was out here. Maybe I'll move this down a little. You wanted to know what G is for this object here. Maybe we'll make it into a satellite. Okay? Want to know what the G is here. Then the R is going to be this radius of the planet plus the altitude. Okay. So then R equals altitude plus radius of planet. So it's like this quantity here is R. Total distance between the center of the two. Okay? Do I have any questions so far?
Yeah, so there's a similar equation for the FG with the big G one, but it has a negative and the R isn't squared. So which one is that?
That is for energy, and that's the last thing that I'm going to talk about. Yes, so if we're talking about the force, we use this. But if we want to figure out the energy due to gravitational potential energy anywhere in the universe, then we use the negative when we don't have the R. And that'll be the last thing I talk about. Great question.
Okay.
Any others? If not, I'm going to keep going. Okay. So, because if we have, this planet, and we can have some object circling it at some speed, we can determine the orbital velocity, which is velocity needed to keep a constant orbit. So to do that, we need to recognize that if we have some object out here, again, we'll call it an astronaut this time, around a planet, and they're in orbit, then the net force on this astronaut, if they're out in space, is just going to be equal to Fg, right? So because it's equal to Fg, and it is a net force, it is equal to ma. Now, because this is probably a little wonky, that's what I'm trying to make it a little clearer. So, okay, that's not too bad. All right, it has an acceleration, but this acceleration is centripetal, because all along here the acceleration is always towards the center, right? Because the force of gravity is always towards the center. So because of that, it's a centripetal acceleration. So it's also going to equal, gosh, that's irritating. More light, less light. There we are. All right. Because centripetal acceleration is equal to v squared over r, it's just another little equation to know. It's the speed squared divided by the radius. That's again centripetal acceleration. So, and this is the tangential speed I should specify. Which, if you're trying to keep something in orbit, is going to be the orbital speed. Okay, so we've got this, but we can rewrite this Fg as g. Again, m, we'll call it, in this case, m of the object, where it's the astronaut, times the mass of the planet, divided by r squared. And that is going to be equal to the mass, because we're talking about the mass of the astronaut, that's going to be the mass of the object, times v squared over r. Now, if we want to know what this v squared over r is, and again, this just comes from the fact that force of gravity is the only net force. Because it's the net force, it's going to be equal to the mass of the object times the acceleration of the object. And in this case, because it's a centripetal force, we can replace that with v squared over r. If we want to solve for this, right, first we do some canceling. Mass of the object does not matter. And we want to isolate this by itself. So we'll multiply both sides by r. And we get v squared equals r times g mp over r squared. One of these is going to cancel. And we are left with g mp over r. If we want, again, to solve for v, we're going to take the square root of both sides.
Michelle Therese, please go to the attendance office for your delivery. Michelle Therese, please go to the attendance office for your delivery.
That the speed is equal to the big G times the mass of the planet divided by the distance between them. Note that we lost the squared because of this r over here. So the velocity, tangential velocity, depends only on mass of planet and the mass, or sorry, and the distance between the object and planet. Do I have any questions on that?
So is velocity tangential? And if so, how do you like represent that on the diagram?
It's like this. It just means like, if, remember it, this all, you know, everything, if you cut, you know, and got rid of the planet, there'd be no force of gravity. And so the object would just want to fly off tangent to the circle. So that is what it would be. And this is also equal to orbital speed. So yeah, that's how you'd show it on the diagram. Something coming off like at a right angle to the circle, like that. Does that answer your question?
Yep.
Cool, cool, cool. Okay. I will also emphasize it does not depend on the mass of the object in orbit. Okay, because that again cancels out. All right. So the last thing I'm going to go through is energy, as you noted, gravitational potential energy. If we are in, so if we are in a constant gravitational field, like on Earth, then we use MGH. And we can use that. But if we are not, if we're somewhere else in the universe, come on. Then we use UG equals negative G M1 M2 over R squared. Sorry, just R, not squared. And that is, again, everywhere. Note, in both equations, as you get higher or further away from from the planet, I guess I'll say, the UG increases. And note also, both objects, planet and other object, must be in your system. Oops, there we are. So in both equations, as you get higher or further away from the planet, the UG increases, and both objects, the planet and the other object, must be in your system. Other. Okay. However, with this one, UG at infinity is going to be 0 because R goes to infinity. Okay, so that's the newest stuff about it. Both objects must be included. As you get higher, further away, you have more energy. You think of, more ability to turn that energy into some other type of energy. As you get higher off the ground, and drop something, that means by the time it gets down to the ground, it's going to have more kinetic energy. As you get further away, you get closer to zero, but still you're getting higher and closer to that as you get further away. Okay? Now, do I have any questions about that? All right. So if I don't have any more questions, then I will, I guess I'll stop recording.